about the type of conic section called the parabola. Now, the parabola is formed when the plane that intersects the parabola is parallel to the slant height. So this length over here, also known as the slant height or the slant length, is parallel to the plane. So basically, it's the cross intersection of a plane which is parallel to a slant height, and that gets us a parabola, as you can see over here. So a parabola is really a conic section or a cross section of a cone, and the plane is parallel to the slant height. Now, in this video, we'll be talking about the geometric properties of a parabola and the definition of the parabola, and then we'll be using the definition and properties to derive the standard form and equation, and then we'll be looking at different types of parabolas. Now, without further ado, let's start off this video by discussing the parabola's geometric definition. Now, the geometric definition of the parabola states that the parabola is the locus of all points in which that locus is equidistant from a given point called the focus and a given line called the directrix. So I guess we don't need this anymore. Let's get rid of this. So if that definition didn't make sense, let's say we had the equation y is equal to x squared, and we were to plot this on a 2x2 Cartesian plane. So let's plot this. And given that this is an even function and it's a parent function, it's symmetric along the y-axis. And so if we were to classify any point along the y-axis as the focus and pick any arbitrary point on this locus, call it point P, and pick any arbitrary line beneath the vertex and call it the directrix, so the directrix, and connect this focus to the point P, or the arbitrary point, and drop a perpendicular and call the point here point D, we would have the equivalent statement of FP is equal to PD. So basically, the geometric definition states that if you were to pick any arbitrary point and connect the arbitrary point to the focus, creating a segment, and drop a perpendicular from the arbitrary point to the directrix, we would create two equal segments. That's what the geometric definition states. So now, how do we actually use, also, I forgot to talk about this. What if we had FP over PD? Well, since they're the same thing, they would be equal to 1. And this idea is called eccentricity. And so eccentricity is the ratio from the segment created from the focus to the arbitrary point over the segment created from the arbitrary point to the directrix. Now, in this case, the ratio is 1. And in fact, for all parabolas, the eccentricity, or the ratio, will always be 1 because these segments are equal. And don't dwell on eccentricity too much, but it's very important. In fact, we just refer to it as E. It's very important in analytic geometry, so don't worry about it too much for now. This is just an introduction. We'll get more advanced later. So now let's talk about how to derive the geometric equation, or the standard form, using the geometric properties. So let's get rid of this. Okay. Oh, that's weird. My bad. Okay. So, to derive this, you know that the line is the directrix, so I just erased it. So to derive this, what we're going to do is we're going to assign f coordinates of 0, p, and then we're going to assign the arbitrary point P coordinates of x, y, and then we're going to assign point D coordinates of negative x, p. And the reason, x negative p, my bad, I switched it. This is going to be x negative p. And the reason why this is x negative p is because obviously since p is x comma y and point P and point D lie on the same x segment, they're going to have the same x value. So basically, since point P and D lie on the same segment, they will have the same x value. And also, we go up p units to get to the focus, so we'll go down p units to get to the directrix, which is why the point D is x comma negative p. Now, we will also define the distance from point F to point D as distance 1, and define the distance from point P to T as distance 2. So in this case, we note that distance 1 and distance 2 must be equal given the geometric properties of a parabola. So what we can do is we can use the distance formula, which says d, or the distance, is equal to x2 minus x1 quantity squared plus, in fact, let's erase this, y plus y2 minus y1 quantity squared. So using this, and this is really just the Pythagoras theorem, you can think of x2 minus x1 and y2 minus y1 as the legs and d as the hypotenuse. So using this formula, we can just plug in the information we need to satisfy this equivalence statement over there. So now so to calculate for distance 1, we say distance 1 is equal to the distance from coordinates 0, p, or point F, and the coordinates x, y, or point P. So using the distance formula to calculate the distance from that, we get x squared plus y minus p quantity squared is equal to distance 1, and then we equate that to distance 2, or the distance from point P to point D. Using the distance formula, we get 0 plus y plus p quantity squared. Now, using algebra, we get rid of the radical and we expand the binomials. We get x squared plus y squared minus 2py plus p squared is equal to 0 plus y squared plus 2py plus p squared. Now, canceling common terms and adding 2py to both sides, we isolate for the x squared and set it equal to 4py. But we note that we usually write it as y is equal to ax squared, meaning that we have to isolate for y. So when we isolate for y, we get y is equal to 1 over 4p x squared. And so this is the standard form or equation of the parabola. And some textbooks might just refer to it as x squared equals 4py, and it really does not matter. These two ways are actually acceptable for the standard form because we just use it to find the geometric properties. Also note that since you don't need this, look at this for a while. Okay, since you don't need this, let me write something important. Also note that P is equal from the distance. I'll call D for distance. The distance from the focus to the vertex and vertex to the directrix. So I'll call it directrix. And so really it's basically this distance over here. And basically the distance from the focus to the vertex or the distance from the vertex to the directrix, assuming that it's perpendicular. And it's also good to note that P is also called the focal length. So it's also equal to the focal length. So textbooks will usually refer to this as the focal length. Now, since we have discussed and derived the standard form, let's look at types of parabolas. let's actually get rid of all of this. In fact, let's just erase everything. Okay, now, there are 4 cases for the parabola. Now, case 1, it opens up, and then, my bad, case 2, it opens downward. Case 3, it opens to the right. In case 4, it opens to the left. Now, in case 1, we're going to use the formula y is equal to positive 1 over 4p x squared. Since the equation is symmetric along the y-axis, or x squared is equal to 4py, and it's positive. So this is positive. And since case 2 is symmetric along the y-axis, or it's an even function, we're going to use y is equal to negative 1 4p x squared. Since it opens down, it's negative. And then we're going to use x squared is equal to negative 4px. Or, it doesn't really matter. And then for case 3, you're going to use, since it's symmetric along the x-axis and it faces to the right, we're going to use x is equal to positive 1 4p y squared. Or we're going to use y squared is equal to 4px. And then for case 3 or case 4, we're going to use, since x is symmetric and it faces to the left, we're going to use x is equal to negative 1 over 4p y squared, or y squared is equal to negative 4p x. And there you have it. We have just talked about the different cases. And thank you for watching this video. Stay tuned. In the next video, I'll probably be doing problems for parabolas and discussing more in-depth detail about this. All right, thank you for watching. Bye.